This is the final part of the 22nd lesson in heat transfer. This lesson has been focused on analyzing internal flow convection heat transfer when fluids are flowing through tubes or ducts of constant temperature at the wall. In this final part of the lesson, however, we will look at how to adapt the results that we have for the constant tube wall temperature case to a more general case when there is some mixed mode heat transfer on the surface of the tube. By the end of this lesson, you should be able to explain how this is done. You should also be able to explain what the UA product of the heat transfer is. On with the lesson.
What if you don't have either an isothermal tube wall or a constant flux tube wall, right, which happens a lot. And you end up with problems like this, which I think is like either 825A or 860, I don't remember, okay? Where you have, like this is a tube, you have heat transfer on the inside because we got fluid flowing through the tube on the inside, but then we also have some other fluid flowing over the outside. So the tube wall is neither isothermal, it also doesn't have a constant flux. It's something in between. Right? The good news is that the way that we handle this case is we kind of say, yeah, well, the tube wall is not isothermal, but here, if we go far enough away, the fluid far enough away from the tube wall is isothermal because it has a temperature T infinity. And so we can kind of apply all the work that we did for the isothermal tube wall and make it work for us here. So how do we do that? So the way that we do that is we represent this heat transfer situation with a circuit. So this is like T on the inside. What T it is doesn't really matter because that T is changing, of course, right? Like it's exponentially changing, or maybe not even exponentially, but actually it is exponentially changing. It's exponentially changing in a flow direction. But we think about the heat transfer as convection on the inside, then conduction in the tube wall, and then convection again on the outside. So we have convection, conduction, convection. So on the inside, we have 1 over h bar I, whatever the average convection coefficient is for the inside, times the area of the inner tube wall. Then we could potentially have conduction through the tube wall. Very possible. It also could be that we're told that the tube is thin enough, right, or the thermal conductivity is high enough that this resistance doesn't matter. And then we have convection on the outside. So times the area of the outside. So that there is some resistance associated with this heat transfer path, right? And the way that we get this is we just add this all up. H bar I, AI, plus the log of RO over RI over 2 pi KL plus 1 over HOAO, right? We add those three resistors up and we get the total resistance. The total resistance has units of Kelvin per watt, right? And we kind of think about, we'd say, well, if I want to get the heat transfer rate, Q, right? Q is just some delta T, right, divided by our total. But we can also think about this as like, we're going to see, as kind of like a convection coefficient times some delta T. And so this R total represents the inverse of something that's called the UA product, right? And this has units of watt per Kelvin. This thing right here is called I literally say UA product. It's the UA product, right? It represents the inverse of the total resistance to heat transfer between the two fluid streams. And what's nice about it is any place that we saw H, it kind of looks like H bar times A, right? Like it's just instead of a U, we put an H, it looks like H bar times A. Any place that we had H bar times A in our isothermal tube walls case, we can swap out the H bar with the U bar. So if I want to calculate how the mass, the mass average flow, the mass average temperature changes in the flow direction, I swap the H bar out with the U bar, and I swap out TS with T infinity. Right, so I would say T infinity minus TMX over T infinity minus Tmi is equal to exp to the minus u bar times p times x over m dot c sub p. If I want to, get the heat transfer rate, I put u bar a times delta T log mean. In other words, you can also think about this. The right delta T for this heat transfer equation is the log mean temperature difference. That's the one I'm going to use with this total thermal resistance calculated this way. Make sense? So those are going to be your conditions for a case that's like this, that's neither isothermal tube wall nor constant flux. It's really a mixed condition on the surface. This, by the way, is like the perfect segue that we're going to start talking about heat exchangers where we have heat transfer between two fluid streams. Okay, we're going to use a lot of these ideas there too. Beth?
How do you find the UA?
How do you find the UA?
Would that just be the...
Yeah, so I would say my answer to your question, Beth, is two-pronged. One, I would say most of the time I don't necessarily care just about U bar. I care about U bar times A. That's what shows up in my equations here, right? Like U bar times A is what shows up. If you do want to calculate a U bar, which you could do, you take the UA product and you divide by an area. But then the question becomes, what area do you divide by? Because there's a different area on the inside of the tube than there is on the outside of the tube. So that actually gets into this nuance, right? Where if you are calculating the U bar, you have to tell me what area you based your U bar on. Because to get there, you have to take the UA product and divide by one of these two areas. And you have to tell me, I divided by the area on the inside of the tube, or versus I divided by the area on the outside of the tube. Okay, but you just divide by one of them and say which one you divided by. Does that make sense?
Does it matter which one you divide by?
Not really. One's going to be bigger than the other, yeah? Because if you divide by the inside area, it's a smaller area, so the U bar is going to be bigger. But it represents this, right? It represents the same thing.